that are on the outside of the back of your refrigerator. And put your hand above the back of the refrigerator. It's hot. So what are we doing? I pump that gas up, I make it hot, I run it out there, and so that the atmosphere in your house can draw away that hot gases from the back of the refrigerator. And then I take that gas, and just like in here, I let off the pressure. The gas expands and gets really cold. And then what does that cold do? Well, that cold is colder than the inside of your refrigerator. So your food, which is hot at 40 degrees, right, gets colder by giving some of its energy back to this, back to the gas. And then you just cycle that back and forth. But no matter what, energy, heat, only transfers hot to cold. We good? Okay. Our thermometers. What was the first thermometer? Out of our scales, with Fahrenheit, Celsius, and Kelvin, which was the first one? Fahrenheit. Okay. What's the purpose of a scale? It's to measure things and to give us a reference. All right? What is the most common scale for humans? 12 to 84? What is it? What is it? What range? What are the top and the bottom of the scale do we use most often? Close. 1 to 100. Actually 0 to 100. But they would have started with 1 because who came up with the number 0? Don't you guys know history? Come on! The Mayans were the first ones to actually use the number 0. Gee whiz. So sad. You feel what? I think you said something. What?
Oh, I was just going to say, I feel like I didn't learn anything.
I absolutely love knowledge. And I find that actually most knowledge connects with something else. And that there is a plethora of just really, really fascinating facts.
It's like cool.
So I know lots and lots of really useless stuff. But I don't find it useless because they all make sense to me. All right, 0 to 100. We use 0 to 100 because 100 things we can understand. I'm not going to use 0 to 10 because 10 is too easy. I can understand 20. Twice 10, that's easy. Right? 0, that's nothing. Not a problem understanding that. Yes? So what's the largest thing we can understand? And we run out at about 100. Visualize in your head right now 100 people. You could actually work that out. And when you look at a crowd in a stadium, you can figure out, okay, that's about 100, I could do that, so there's like 500 in there, and you can estimate. But you're not going to go larger than your unit of about 100. That's what we understand things. All right? So when we do the Celsius scale, what's the range of the Celsius scale? Now, it goes off in both directions for a long ways, but what is our range? What did we do? We made it 100. And what's the top and bottom? What's the 0 and 100 of the Celsius scale?
Freezing, boiling.
Water freezing, water boiling. Why'd we do that?
Easier to understand. Reference.
Common's going to be a better one. It's easy to understand, I agree, but it's one that can be replicated anywhere on Earth. Under the same pressure conditions, because we have to be at 1 atmosphere. Right? You do understand, I could have boiling ice water. I can have water that is cold enough to be freezing, that it is changing from solid to liquid, and it will be boiling at the same time. Literally boiling. And the faster it boils, the faster it freezes solid. You know how you do that? It's called the triple point. Lower the pressure. I take a glass of water with ice in it, comes to thermal equilibrium, so I have both water and ice. That means they're at the same temperature, right? And that's usually what we do with our drinks. We put the ice in it, and then it stays at 0 degrees for a long time, right? But the ice continues to melt. Okay, I put that into a vacuum jar, start pulling a vacuum, and eventually, as the pressure gets low enough, I will have boiling water. And yet, it's freezing water. So I can have boiling, freezing water. Boiling ice water. Kind of cool. That's a joke. Kind of cool. No, just don't understand. That's okay. It also means this type of concept. If you go high enough into a mountain, you climb a mountain high enough, you cannot boil an egg. Because the water will boil at a temperature less than the protein in the egg will solidify. Now that doesn't mean you can't cook an egg, because fire is still fire, right? You can fry it, not a problem. You just can't boil it. And that deals with Herbert equals nerd. Okay? And we're dealing with the surface tension, and there's a lot that goes with that, but it's still going to deal with what our pressures and temperatures and all of those things are. Okay. So Celsius, we divide out 0 and 100, right? And the 0 is the freezing of water. The 100 is the boiling of water. What do they do with Kelvin? Right, all they did is we're going to set up this equation, and we notice that we have these two numbers, that if pressure goes down, volume goes down, and if pressure goes down, volume goes down, and if pressure goes, or temperature goes down, volume goes down, and they kept lowering the temperature until volume hit 0. It doesn't actually hit 0, but graphically it hit 0. And when it hit 0, they looked at what the temperature read. And what did it read? Minus 273. Right? Can I have a negative volume? So they figure I can't get less temperature. Therefore, that's the absolute lowest it goes, so they called that absolute 0. But it was still based on the Celsius temperature. So what was the Fahrenheit scale based on? Where's 0 Fahrenheit? It's freezing salt water. Freezing brine. Right? Because it's minus 32. I mean, it's 0 degrees Fahrenheit, but water, fresh water, freezes at 32. So 0 would be less than that, right? And that's a repeatable number. Where's the 100? No? Oh, salt water boils at more than 100 Celsius, right? Remember your K of depression and K of elevation? That when you have molality, right, when whatever your molality is times whatever your constant is the change in temperature of its, up and down. That's chemistry, right? Right. So salt water boils at more than fresh water does, just because we have moles in it. Which y'all did celebrate Mole Day yesterday, right? At 6:02 in the morning and 6:02 in the evening. At 6:02, 10:23. Anyway, okay. I'm trying to do this fast and I just can't. The 0 is freezing brine, which was repeatable. Okay. What's your body temperature?
98.6.
98.6. If you round that because you don't have accuracy, what's your body temperature? 100. It's repeatable. And we do things in 0 to 100. That's the human scale of things. All right? Now, y'all know how to convert between Celsius and Fahrenheit and Celsius and Kelvin and Celsius. And you never convert from Celsius to Fahrenheit. I mean from Kelvin to Fahrenheit, sorry. Right? You go from Kelvin to Celsius to Fahrenheit. But so you can do all those. I'm assuming we can do that and not do that. I'm not worried about that. Okay, 0 at law of thermodynamics. I find this funny, right? The scientists were coming up with the first law of thermodynamics and the second law of thermodynamics, and they had those. And then they realized, oops, there should be one that came before that. And since they already had the first and the second, what would be one that came before it? Zeroth. So it's not a zero temperature number, it's a zeroth because they'd already named the first and the second. No, because they said this is what they were. It was so entrenched. And okay, when we do circuits, we're going to find what we call conventional current. All right, when everybody who was back in who was the United States' most famous person involved in understanding of electricity? Benjamin Franklin. And you know the stories and things like that, right? You do understand he was not the one flying the kite. Okay? Right. It was his nephew. Why he didn't like his nephew, I don't know. But it was his nephew flying the kite. Just, right? It gives you an idea of when this conferences and when these things were when these were happening. All right? But in the early 1800s, all of the scientists from wherever they could find them all got together in Europe, and they're trying to figure out this stuff that deals with this electricity or electris or something fluid. There's a thing that Benjamin Franklin called it. Whatever it is, right? And they had a choice. They could figure out things. They first of all knew there were two types. There was something. They could have called it orange and blue. Because on a color wheel, orange and blue are opposites. And they knew what they were opposites. But the simplest opposites they have is plus or minus. So they're calling them plus or minus. And they knew they could create an effect. If they took plus things going this way through a wire, they get a certain effect. But if they took minus things going this way through a wire, they got the same effect. And so which was it? Was it plus things going through a wire or minus things going through the wire? And they didn't know. They honestly had no clue. Right? And so they made a choice. They decided, we're going to say that it's positive charges moving through the wire. So, if in your house you have positive charges moving through the wire, what does that mean? It means your house is on fire and your wires are melting. Because where are the positive charges? Protons. Where are protons? In the nucleus. And in my copper wire, are the nuclei moving? No, it's the electrons that are moving. So I actually have electrons going one way, but conventional current is positive charges moving the other way. But if you actually have positive charges moving in your wire, that's a bad thing. Y'all follow? Now, can I have a flow of positive charges? Sure. I can. That's what CERN does. They have protons moving in one direction. Right? And for CERN, they actually have a set of protons that are going in this big circle going this way. Right? And they have another set of protons going in a circle this way. So they have two opposite currents. And so they have the big circles of protons, and then they smash them together. Right? And we're going to talk about the fact that in this part, AP2, you need magnets to bend those charges to move. They're not in wires. They are in a vacuum. They're in a tube that has nothing in it. All right? But they have a vacuum, a magnetic field that gets the protons to go in opposite directions. And then they crash them together and do a bunch of stuff. So we will deal with that. But the concept of going back to it's the first law, second law, we still talk about conventional current. Do we know that it's electrons going the other way? Yes. Doesn't matter. Current is the flow of positive charges. It's a lie, but it's the lie that everybody chooses to believe. And we do everything from there. So why would they? It's just... you also understand that for science to progress, all the old people have to die. It's true. And I'll give you an absolute truthful example of this, right? You all know when I talk about CERN, what I'm talking about? The project in Europe? Okay, it's the Center for European Nuclear Research, but that's research nuclear. That's C-R-E-N. C-E-R-N. Man, I can't spell. And I still have 5 to 9 to be a jack of the box, and it's going to be a long night, right? Center for European Research Nuclear, C-E-R-N. It is where we are looking into what the atom is made of, what quarks are made up of. We're looking for the Higgs boson. Why do we have gravity? How does gravity work?